Good evening, everyone. So, welcome to my YouTube channel, Maths. So, today we are going to see fifth lecture on probability theory. In this lecture, we will study independence of events. So, independence of events. So, let S be a sample space. And A and B are subsets of S. So, A and B are subset of S means what? A and B are events. Okay, events. Then the event B is said to be independent of the event A if P, the relative event B event A is nothing but equal to the probability of relative event B relative to A is nothing but equal to probability of B. Okay. So it means taking probability of B with respect to A as a relative probability, it does not change the probability of B. Okay. So if we take probability of B with respect to relatively to A, the probability do not change. It remains B. Okay. Okay. So now I am writing a result. So you can say result, you can say proposition. Let S be a sample space and A be subset of S. It means A and B are events. Then B is independent of A if and only if A intersection B is equal to PA into PB. Okay. So let's see the solution, or you can say proof solution. So first, suppose that B is independent of A. B is independent of A. So this implies P, the probability of relative event is equal to PB. But by definition, what is this? This is nothing but PB intersection A upon P. This is equal to PB. So this implies I can write B intersection A or A intersection B, both equal, both are equal. Either you B intersection A or A intersection B, both are equal. Okay. So this is equal to P A intersection B is equal to P A P B. Now conversely assume that P A intersection B is equal to P A P B. Okay. We have assumed the converged statement and we will show that B is independent of it. Okay. So now what we will check, P B relative probability of relative event P B intersection A upon P. What is this? I can write P B intersection as A intersection B upon P. Now put the value of this P A P B intersection, which is equal to. Okay. So this is cancel out. So what you got? You got this is equal to P. It means you got P probability of relative A, B relative A is equal to PB. This implies B is independent of A. Okay. Another remark, I'm writing a remark, or you can say another proposition. You can say let S be a sample space and A and B are subset of S. It means A and B are events. Then B is independent of A if and only if A is independent of B. B. Let's see its proof. So B is independent of A if and only if, this is the symbol of if and only if PA intersection B is equal to PA into PB. Okay. Now, same thing. What is the meaning of this? We can say this. If I write here, A is independent of B, then what I will write? Yeah, when it will happen, if and only when P, you replacing A by B and B by A. So what you will get? PA intersection A is equal to PB into P. But both these statements are same. Both these things are same. Both are same. So you write A intersection, B intersection, or you can change their multiplicative order. Things are same. So what does it imply? B is independent of A if and only B is independent of A. Okay, sorry. A is independent of B. So this is proof. Okay. So in the so we will so therefore now remark, since B is independent of A uh, of A if and only if A is independent of B. Okay, we write the independence of events, independence of events. We write the definition of, we write the definition of independence of event in the following way. So same definition can be written in the alternative way, but things are same because we know B is independent of A is saying that A is independent of B, and A is saying that A is independent of B is saying that B is independent of same thing. Okay, so we write in a following way: independence of events. So in the definition of independence, I would like to add one more thing, that so I have written that a B is said to be independent of A if B, the relative probability is equal to, the relative probability of B with respect to A is equal to PB. Okay, then B is said to be independent of. Otherwise, B is said to be dependent on it. Okay. So now we have shown that if B is independent of A, this implies A is independent of B. So now we rectify our definition. Rectify definition is same, but we have we prove more things. Okay. So let S be a sample space and A and B are subset of S. It means what? A and B are events. Okay. Then A and B are said to be independent if A, P is equal to PG or PA is equal to P. So this is done. Okay. So this definition is done. Okay. Now we will do some examples. Okay. So example number 1. A dice is thrown. Okay. Sorry. I should write. Two cards are drawn from a deck of cards. Okay. In succession. Okay. Consider the events. Consider the events. So with replacement, replacement means we draw a card and after drawing we put it again in the deck. Okay. With the replacement. Okay. It means card is drawn and after drawing, before drawing the second card, we put first one into the deck. Okay. Consider the events. A, the first card is the first card is an S, B. The second card is spade. Card is spade. Okay. So are the events A and B independent? Okay. So we will check. Okay. Solution. So what is the probability of A event? We are choosing a S. The first card is drawn is S. S are fours. So number of A upon number of elements in A, number of elements in sample space. So we have 4 aces and third consecutive cards we have. So what we have? 1 upon 13 we have. What is PB? How many spades we have? We have 13. Okay. So what is this? NB upon NS. 13 spade we have, 52 cards we have. So this is 1 upon 4. And what is A intersection B event? It is nothing but what is this event? This event is the card, the first card, the card is S and spade. So what is this probability? A intersection N S and A intersection B upon NS. So what is this? Card is S and spade. So how many is S and spade? Both. So we have only 1 and upon 52. Okay. So now check whether PA. So this implies PA intersection B is equal to 1 upon 52. Also, PA into PB. What is this? PA is equal to 1 upon 13 into 1 upon 4. What is this? 1 upon 52. Okay. Okay. So this implies PA intersection is equal to PA into PB. So this implies A and B are independent. Okay. So this is true. They are independent. Now I am considering another question example. Okay. Another example I am considering. Example 2. A dice is thrown. Okay. Consider the event. Events. We are considering this event. A is equal to getting number perfect square. Okay. Square. B, getting number greater than 3. So my question is that are A and B independent? So listen, let's see. So what is S actually? S is 1, 2, 3, 4, 5, and 6. So what is A event? A event is getting perfect square. So which numbers are perfect square in this S set? Tell me. A is equal to 1 and 4. Only these two numbers are perfect square. What is B? B is the number getting greater than 3. So 4, 5, 6 are greater than 6. So now what is A intersection B here? It is nothing but 4 only. So what is PA? PA is NA upon NS. That is 2 upon 6. That is 1 upon 3. Okay. And what is PB? PB is equal to PB is equal to. So I am taking here greater than 3 and less than 6. And less than 6. I am taking this event. So what will be here? B event will be here. What will be? It contains only 4 and 5 elements. So we have event B greater than 3 and less than 6. Okay. So A intersection B contains only 1 element. So what is A? 1 by 3. What is B? And B upon 2. And B upon NS. That is 2 upon 6. What is 1 by 3? And what is P? A intersection B? And A intersection B upon NS. That is 1 upon 6. Now you see that what is now PA into PB is equal to 1 by 2 into 1 by 2, that is 1 by 4. So this implies PA intersection B is not equal to PA PB. So this implies A and B are not independent. They are not independent. It means what? They are dependent. A and B are dependent. Okay. So today's question up to this, we have discussed this lecture. If you have any problem related to this lecture, you can comment on my YouTube channel. Like, share, comment, and subscribe my YouTube channel. So thank you very much for today's lecture. Thank you. We will see you in next lecture.